Thank you everybody for coming. My name's Trey Grainger. Today I'm going to be talking about extending Solr, building a cloud-like knowledge discovery platform. I work at CareerBuilder. I'll tell you about myself in just a minute. But the general overview for this talk is a couple different areas. I'm going under the assumption that most of you could care less what CareerBuilder does, that you're more interested in how we're using Solr, so that's what I'm going to be talking about. If you want to talk about CareerBuilder, you can talk to me afterwards. So I'm going to talk about three main areas. One is several approaches to handling multilingual content. So there's various approaches which have been kind of thrown out there. Some are good, some are bad, and it really depends on your use case. So I'm just going to do a quick overview and tell you what we're doing. I'm also going to talk about some custom scoring implementations that we've done, things that you may find useful dealing with payloads, and if you need to account for somebody trying to spam the search engine, how you can account for that. And then the majority of the purpose of this talk is to actually talk about a cloud-like service which we've built on top of Solr, which has significantly increased our agility and ability to deploy Solr-based solutions. So I'm going to talk about that and the benefits of it. And then at the end, I'm going to talk a little bit about the future, some of the things we're doing with data analytics that you might find useful, and then I'll take questions. So I'm Trey Grainger. I'm the Search Technology Development Team Lead at CareerBuilder.com. My primary background is search and recommendations. I have also done kind of every part of the web application stack. I've got a side project which I do for fun, which is a gluten-free search engine and networking site. And so that gave me the ability to kind of stretch the breadth of my skills. But for the most part, high volume interior architectures, relevancy tuning, and a little bit of machine learning are some of the things that I've done with search and with Solr. So to tell you about our scale, we're not at Twitter scale, but we're relatively large. We've got about 1 million new jobs each month that flow into the system, over 40 million resumes, that's constantly growing. And we've got several other types of data which go into analytics as well. Tens of millions of more documents. So we've got about 150 globally distributed servers across the US, Asia, and Europe. And we've even got some cases where we've got dynamically generated Solr cores per account for some of our customers. So we end up with thousands of dynamically generated cores in some instances. And then we get about 1 million searches an hour, a good bit more than that for peak load, but and about 100 million documents across our framework. Some of them are relatively large. Some people have really long resumes, but there's a lot of good meta information in there we extract out as well. In terms of products we offer, kind of search-based solutions, we've obviously got job search. Many of you have probably used our job search capabilities. We've got a resume search engine as well, where recruiters can come in, and if you've said that you want your resume to be public and for companies to be able to search for you, then they can actually search through. I try to protect whoever's resume this was. We also allow you to search through your talent intelligence pool. So if someone applies to your job, or they say, hey, I'm interested in following your company or something like that, we can actually allow people to search through those people as well. So maybe someone applies to your job and you don't have an opening at the moment, but a year later you do, you can go back and look at people who were previously interested. Then we do standard things like autocomplete based off of Solr, geospatial searching, and recommendations. Recommendations are actually really important for us. We take all jobs, resumes, and even users to some extent and try to classify them and use that classification information to recommend other jobs, resumes, etc. We use a combination of collaborative filtering, so based upon the actions of other users who took similar actions to you, what jobs are you likely to want to apply for, things like that, as well as, like I said, some kind of in-house classification techniques. And we've also customized scoring, which I'll talk about in just a bit, using payloads effectively apply different weights to the same content, to content within the same field, as opposed to having to search across multiple fields. And then recommendations, I don't know if this is standard or atypical, but our recommendations are largely driven off of search with the meta information and classification data we have, as opposed to being done offline with Hadoop or something like that. So users can actually get real-time recommendations for anytime they come to the site. It's an example of job recommendations for search technology development at CareerBuilder. So you see similar types of jobs you might be interested in. Also resume recommendations if you're a recruiter and you're looking for someone who matches a resume you have or a similar person you found before. I told you a couple of main areas I wanted to talk about. The first is multilingual analysis. So there's a couple of different approaches. Let's say you've got content and it's only in English. Okay, well your job is easy, right? You create a field, you use an English stemmer or lematizer, and then you're done. But let's say you've got content in multiple languages. Well, you've got a couple of different options. First option, which is the most commonly recommended, is have a separate field per language. So you've got a text_en for English, text_de for German, etc. for all the languages you have. This is the simplest and easiest to implement, probably the reason it's recommended the most. But depending upon how intelligent you are in actually indexing your content, you might have to keep multiple copies of your content in different fields if you're not sure up front which field it was supposed to be lemmatized or stemmed according to. And then also, if you're searching across a lot of fields, dismax style, that can actually get really, really slow after you get past a few fields. If every search you're issuing has to search 5 fields, that's like 5 sub-searches as opposed to just searching on one field. So another approach, which many of you have probably heard of, probably some of you have even used, is to have a separate Solr core per field, or per language, excuse me. So for example, you would have one Solr core that had an English stemmer, you would have another Solr core that had a German stemmer, another one for Chinese, and then when you actually search, you would do a distributed search across all of them, and each core would stem or lematize according to the particulars of what data is in that core. So it's actually a really useful and novel technique because at query time, your searches can be language agnostic. You just send your search and it goes everywhere, and each independent Solr core processes as you would expect for the language that's resident on it. Obvious disadvantages are if you've got multilingual documents, like I've got a document that's both Greek and English because everybody in Greece speaks both languages. Then I have to either send it to both cores, in which case I've got a relevancy problem. If one shows up higher than the other, it messes with relevancy a lot. Or I have to actually create a new core, which is my Greek and English core, in which case you've got to do some complicated analysis to be able to handle both. So, but that is another option if you don't have really multilingual content. You've just got a lot of different content in different languages, but not the multiple languages per document. And then the third option, which is what we use at CareerBuilder, is actually putting all the languages into one field. So, for example, if this is my input, which is Ion Anto, I'm not going to read the Greek. Basically, this says, if you're looking for a brilliant professional career, CareerBuilder is one of the U.S. compañías hiring search engineers. So what you can see, right, there's some Greek here. There's a lot of English. Here's a Spanish word thrown in for good measure. And then what I'm actually doing is I'm passing in the languages that I want to process in. And then I actually have a sort of multilingual token filter or tokenizer, which can take each of those, find the root form in each respective language all the way through. And you'll see for Spanish, compañías became compañía. Engineers for English became engineer, etc. So by doing this, you actually get kind of the best of both worlds because you only have one field you have to search on, and you still get all of the languages. And at query time, if you want to, or index time, you can specify the specific languages that you care about. So if you've identified the languages in your document, you pass those in at index time, and then at query time, you can also pass the same languages in and query accordingly. So for our use case, we actually know what language is someone searching in. For example, we've got websites in dozens of different markets, and if you're on the French website, we know you want English and French. If you're on the EU website, we know that you want English, French, German, et cetera, for all of the EU languages. In the US, it's typically English and Spanish, mostly English. So we have a good use case because we know up front what language we need to look at. But also, if someone searches in a location geographically, we actually have languages mapped to location. So if someone is in the US and they search for something in Paris, we say, oh, hey, we should probably add French as a language because we know the people in France speak French. So depending upon your use case, you may or may not have access to this information at search time, and that might be something that would prevent you from using this. But if you do, this can actually be a really useful technique for not having to do crazy stuff across multiple cores or multiple fields. And just a general strategy, if you are going to do this, what we do is we take the token stream that's coming in, we copy it, we then run it through each stemmer or lematizer for the respective languages, and then when we're done, we just stack them all on top of each other. So if you saw the middle steps in here, you would actually see a lot of duplicates. We just run the duplicate token filter, and it shrinks them all back down to what you would expect. Here's a slight use case study. Just want to mention stemming versus lemmatization here. I think most of you probably know the difference, but if not, stemming is, hey, I take the word dries and I chop off the ES and it becomes dry. This is using the standard, I think, Snowball or the Porter filter that you would get in Lucene or Solr, versus lemmatization actually finds the root form. Stemming's easy. It's already there in Lucene and Solr. You can make use of it. Most of you probably are. Lemmatization is a lot harder problem. There's companies here like Basis Tech and some of the other, I know Symtext has like a morphological analyzer, and was it Intrafind? Anyway, there's several companies that can do this type of thing. If you really want to do this, go for it. If you've got the budget, you might want to pay someone else to do it for you. But this is just a general use case study that we did when we were converting from our old search platform, which is a very commonly known commercial enterprise vendor. You could look up CareerBuilder and tell who it was. But basically what we did is we said, all right, that's going to be our baseline for what is good in terms of linguistic analysis and recall. And then we tried a couple of different techniques to see how different options compared. So for example, here's the commercial vendor. Here's Solr with some commercial and open source kind of combinations for actually doing lemmatization. Let's see how they do. And then let's actually take the built-in lemmatizers, the built-in stemmers in Solr and use those, and then let's do nothing at all. And then K-stemmer was a special one because that only applies for English. So basically what we found is for what we would expect to come back, using lemmatization, we got about 4% more than we did with the commercial vendor, and about 3% less. This is like the overlap. So 90 whatever percent is exactly the same, but we got 4% of things back in Solr that we weren't getting before, and 3% less that we were. Same thing for Snowball, etc. So what you see here that's interesting, right? Greek's an anomaly because our previous vendor didn't do well with Greek at all, but for the most part, let's just look at English. This is about what you would expect. This is what we expect to come back. So we've actually, over doing nothing, if we do nothing, we have 48% less results coming back than if we use lemmatization. And if you flip that on the other, on its head, doing nothing versus lemmatizing, you get 92% more recall. Basically, the point of this, just to throw it out there, is that if you do actual lemmatization, finding the root forms, you can significantly increase your recall, in our case 92% for English, while not hurting your precision very significantly at all. You'll see that for Snowball, when we use that, we actually got 28% of stuff that more or less was garbage. So by being overly aggressive, you're getting a lot more recall, but your precision is going down by a good bit. So that's something you might want to consider when you're weighing the pros and cons of doing more advanced lemmatization versus stemming. I will say the case stemmer actually seems to do a relatively good job. So if you're doing English content and you can't afford something more sophisticated, then I would recommend the case stemmer, but it depends on your use case. Custom scoring. So in addition to linguistic analysis, one of the things when we were switching from our previous search vendor to Solr that we needed to do was account for some more sophisticated scoring, I would say. So there's a couple of typical ways that you would actually boost content in Solr. You can just do it on a per term basis, boosting particular search terms. You can also boost particular fields and say if I have a match in this field, I want it boosted higher. Those are the two typical ways of doing it. You can also do index time boosting. We don't because we want more flexibility to be able to change our relevancy on the fly, and index side boosting doesn't really give you that. You have to re-index everything. But what we've done is we've actually modeled the ability to have basically fields within fields by using payloads. So what we do, we have one field that has all of this content in it, but this word has a payload of 1, no payload, no payload, no payload, payload 3, 3, 3, 2, 2. These are encoded into a byte, but you get the idea. But what this gives us is the ability at query time to actually say, hey, any matches in bucket 1, I want to actually give a higher boost to, a boost of 10. So a lot of people will use payloads to hard encode their boosts. We've abstracted it out one step further, which is instead of hard coding a boost, we hard code a bucket, and then at query time, we will actually we'll supply values to map a bucket to a boost. So what this means is that on the fly, anytime we're running a query, we can pass in, hey, I want bucket 1 to get a boost of 10, bucket 2 to get a boost of 1.5, bucket 3 to get a boost of 1.5 as well. We can do those kind of manipulations at query time. And the really great thing about doing this is we can easily do A/B testing. So I can take a subset of users, give them one set of bucket weights, take another subset of users, give them the control group bucket weights, and then I can actually see which group performs better from a relevancy standpoint, and then implement those. Like you could actually imagine abstracting that out to have like a genetic algorithm which was constantly trying to tune your engine based upon what provided the best relevancy. We haven't gone that far yet, but I hope I can do that. Anyway, one issue we have is people are constantly posting jobs on our site, and everybody thinks that their job is the most important and should show up at the very top of all the search results, right? Like with most search engines where you have people trying to get in your search engine. So what some people do is they come into the document and they say, hey, this is a job for a software engineer. So at the very bottom of my job posting, I'm going to say software engineer, software engineer, software engineer, and they just load the page up with these things, knowing that the more times they have the words in there, their term frequency is going to shoot through the roof and they're going to show up at the top. So we have to counteract that. So the way we actually do that, I already told you that we're using payloads for these buckets. What we do is we say per bucket, we have some limit that if you pass that limit, we're either going to reduce the overall relevancy or we're going to just throw you out completely and say, hey, you don't count for that term because you're spamming us. So effectively what we do, we override the payload term query and we tie in custom scoring there. And our payload score essentially becomes the bucket boost, which is the weight of the bucket, how important that bucket is, that field, and then multiplied by how much, we call it a hit map, but basically the number of hits per bucket, we have a function which maps that to some value. So maybe the first hit is really important, so you get a weight of 1 for that. But then once you get your second hit, well, we don't want it to be twice as important, so maybe it's a 1.25 for the total count of the weight of having multiple terms. And so what we can actually do then is generate any kind of curve for relevancy. So say you have a keyword 5 times, and we say, well, 5 is the max. If you have 6, we think you're spamming us. So we're actually going to decrease your relevancy slightly. So for each additional time you match that term, instead of getting more boosts, we can actually start to decrease you until you kind of get in the hot spot of what makes sense for a typical job. So you can imagine building functions where you have like a bell curve where the more hits you get, it's really good up to a point and then it starts going down. You could do linear, bilinear, linear with some kind of drop-off, or you could just have a complete custom map for each individual hit. It will map to a certain contribution towards the relevancy. That's our scoring model, or at least some of the changes and additions we've made to Solr that you guys might find interesting. Additionally, we've built a search cloud on top of Solr, which is kind of the main point of this talk. And the point of the search cloud, there was three key goals when we architected this. The first was to make search easy to use and accessible to all engineers, not just the search team, right? So if someone wants to use search for some specific use case, typically, right, well, if you want a new field, all right, well, one of your search guys has to go add a field to the schema. You've got to restart that instance of Solr. You got to do all this stuff. And the search team really becomes, at least in our case, the bottleneck for getting things done. And so there's a lot of things that should use search which don't, because it's just too much of a hassle to actually make those changes. So the goal was any engineer at CareerBuilder, knowing nothing about search, can set up their own little virtual search engine in a couple hours. And that's it, and make use of it for whatever they want. So obviously to do this, we have to have some way to kind of abstract out the schema out of Solr and make it completely generic. So obviously that's not hard to do. If you've used dynamic fields at all, you just create a dynamic field for a specific type. So effectively our infrastructure uses nothing but dynamic fields. Everything that goes into Solr, the schema is exactly the same in every single one of our 150 Solr instances. There's no difference. Everything just maps into a dynamic field. And that way, in our application layer, we can actually create virtual schemas on the fly and pass that information in. So this has huge yields for being able for developers to rapidly innovate, right? I can write some code in just a minute, and I'll show you in just a second all it takes to do this. Well, I'll show you now. So, all right, let's say I'm some developer and I want to use search. What do I have to do if I'm working at CareerBuilder? Well, first of all, hope you guys can read this. If you can't, the slides will be available later. First of all, you have to create a schema. You create a document. You say search engine.add document, passing in your document. Then you create a search criteria. You say search engine.search. And then you say search engine.delete my document. This is the full example. This is how you use our API. So this plus creating the schema plus creating the document, that is all the code you have to write to create your own virtual search engine. You can probably do that in 10 minutes, and you're up and ready to go. So you can see how this can significantly increase our agility for our engineers to be able to just create something on the fly, especially for prototyping. But this scales as well. We've got an instance where someone's got 60 million documents that they're flowing into this, and it's actually being distributed for them behind the scenes. So we've got this cloud architecture where all the engineer knows is, hey, I've got some pool, it's like a developer key, and I'm going to send stuff into my pool, and I'm going to search it, and that's all they know. They don't know anything about Solr or the internals. And to that point, this is how you create a schema. You say, I want to create a schema. It's going to be called test schema. It's going to support English. I'm going to create a field. It's going to be a string field. I want it to be searchable, retrievable, sortable, and facettable. Add the field to my schema. All right, I'm going to create a delimited text field where the delimiter is a semicolon. I want it searchable. Add my field. I want to create a field that supports German and English combined. And it's going to be a free text field to search on. This is the name of the field. And it supports German and English. Make it searchable. Set a boost of 1.2. Add it to my schema. I want a Boolean field. I want it searchable. Add it to my schema. And you do this, you create the schema. You can keep it around as a singleton if it never changes. If you want to be changing it on the fly, if that's actually useful for you, then you can. But otherwise, that's how you create a schema. This is how you create a document. You take in your schema. You say, I want a new document, passing in the schema. I want to set this field to this value, this field, this value, this field, this value, this field, this value. So I created my schema, created my test document. I say search engine.add document. The infrastructure knows where to send it across our distributed architecture. It knows how to back it up, how to send it to the search engine, all that information. Keeps a persistent store and database table. And then when I delete it, it sends out the delete distributedly, and that's all you have to do to create your own virtual search engine. So And then when you get your results back, after you say search engine.search, a query result object comes back that processes the results and gives you facet objects and all the kind of objects you would expect. And then behind the scenes, like I said, we have a distributed architecture handling queuing of all documents to the appropriate data centers, feeding the clusters, load balancing searches between all available clusters for the given search pool. So we build all of our redundancy in it at that level. So that's our cloud-like search architecture. And then the last section here I want to talk about, and you guys can ask questions about any of this afterwards, but is some of the kind of forward progress we're making in terms of data analytics and also some options for actual knowledge discovery. So this is an example of a product that we launched in January, which is using that cloud-like API that I told you about. And basically my team did nothing but built the architecture and said, hey, you guys, build whatever you want. You can change your schema, you can change your content, do whatever you want. And they basically have built this supply and demand data portal. So effectively, right, we have job postings and we have resumes. What can we do with that data? Well, we can generate charts of, is the field growing? How many people are available in a particular market? We also know how many jobs are being posted, and we can actually generate supply and demand graphs of what that looks like, right? So for California, right, it's very hard to recruit people for whatever the heck I searched for, which was software engineer. So, right, there's a huge demand for software engineers. So if you're a recruiter, let's say you're a recruiter and you want to go to a career fair. The question is, where should I go? Well, let's look. Easy to recruit. Any of these places that are dark, it's pretty easy to recruit, so you might want to focus your efforts there. Let's say you're a contractor and you have to be able to price out labor for some big project you're working on. How do you know how much it's going to cost for the people? Well, we've got salary information. We can tell you per location what's the salary, how hard it is to find people, and probably projecting out what it's going to cost you to be able to price that job. We can generate maps on a month-to-month basis. What's the percent increase? Like, for whatever reason in Raleigh, there was a 400% increase in, I think this is job postings in the month. So probably some bank decided they want to hire. I don't know. Labor pressure trends. You can see year over year what things are doing. So if you want to talk about like coming out of the recession, what things might look like in terms of the job market, all the data is here. And the beauty of this is all of this is driven off of Solr. Basically imagine doing a search, getting a bunch of facets back, and not caring a thing about their actual results. You want to do keyword searches, you want to get the matching for engineer and engineers are the same thing. You want to get all the things you get with search, but you want to actually get a bunch of meta information back that you can chart and graph. So you can see, I don't have it on here, but you can see the top companies, the top job titles, the top whatever for your particular search. So this is one way you can actually use Solr for analytics, something that we're doing right now. Oh yeah, and salary information, right? I didn't want to put software engineer salaries on here just in case I offended anybody in here if you saw something you didn't like. But for nurses, you can actually see breakdowns of where salaries fall, given years of experience, all that kind of stuff. Again, you can do this with facets and some additional tweaking. And then one last area, so we're not doing much with this at this point, but in terms of knowledge discovery, right, you've got a bunch of content sitting in your search engine. This is just basic like caret to clustering, but the question is, well, let's say that I do a search for nursing and I take the results that come back and I say, hey, cluster these for me. What can you actually learn? So in this particular case, right, obviously if I search for nursing, nurse is going to be the big hot topic word. You would expect that. But you also see nurse case manager, registered nurse, nursing supervisor, charge nurse, staff nurse, and you see some noise as well, right? Coordinator by itself doesn't mean a whole lot. Assistant by itself doesn't mean a whole lot. But within this context, you can actually see a layout of what this industry looks like from an employment standpoint, from a job title standpoint. So it's got kind of a nice, clean layout. You could superimpose salaries on top of this if you wanted to see, like, hey, I bet that assistant nurses and LPNs make a lot less than registered nurses who make a lot less than directors of nursing, for example. But also, you could compare it against other industries. So if I search for .NET, you see there's these massive overlaps between all these different groups, indicative of the fact that in IT, people's skills are all over the place. Like, you can have 5 engineers in a room, and they've got 3 languages in common, and everyone's doing their own thing, but there's kind of a shared knowledge base. So again, you can take this to find similar concepts to something you're looking for. So at a macro level, this is interesting, but there's something someone at CareerBuilder used to talk about, which is Hyperion development. And I'd never heard of Hyperion. Apparently it's some kind of business intelligence tool. So I typed it in. I said, hey, cluster this thing for me. I just want to know what the heck this thing is. So it came back with business intelligence, financial, Hyperion developer, Hyperion S-base. I assume S-base is the name of some form of Hyperion something, their software probably. Hyperion consultant, Hyperion administrator. So you get the idea that this is some kind of business intelligence solution that's used a lot by finance, something like that, which is more or less accurate. So this is an example of, I've got a bunch of content sitting there. There's relationships between it that I don't know about. What can I learn from my content that I could then maybe take back to use for things like recommendations, right? Like, hey, I know these things are related, so maybe I'm going to use these as links between documents as part of my recommendations, right? You can do collaborative filtering, you can do hierarchical classification, but what about these sort of mini links between documents? Can you make use of those? So just an example of Solr's not just for search. Like, to think of it as a search engine is not giving it enough credit, in my opinion. It's really a relationship finding engine, right? You're searching for a term and you're trying to find which documents are the most related to that term. You've got a bunch of content and you're trying to find relationships between the content. So I think there's a lot of really interesting things that you can do harnessing the search technology that Lucene provides. So these are just kind of some examples. So I'm going to leave time for questions at the end, and I can do some demos and examples and stuff as well. But general takeaways. So linguistics, right? I talked about lemmatization versus stemming. Know how your linguistic strategy is going to affect your precision and recall, right? Like, if you do anything other than doing nothing, then your recall is going to go up. But unless you do something stupid. But it might significantly affect your precision. So you want to know that, right? Like, maybe if you are using stemming, you want to say, hey, I want the exact word to be boosted in a field that's boosted higher, or in a bucket that's boosted higher than any stemmed version. Maybe that's good enough. Maybe you say, hey, I really want to do some more sophisticated textual analysis to try to hit the sweet spot of precision and recall. But know how to tweak that for your domain. Also, in our case, we built a flexible software API that basically turns Solr into effectively software as a service for anybody at CareerBuilder to use, which has greatly increased our agility, right? Like, things that used to take us with our old search vendor weeks, or in some cases even over a month, now we can do in hours or days, right? I write a few lines of code. I've got this new search field in Solr that's being distributed out across my entire architecture. I didn't have to redeploy servers. I didn't have to shut anything down. I didn't have to get ops involved. It's all software. Makes prototyping really fun. And then lastly, search isn't just about finding and navigating content. It can be used to learn from it as well. There's, again, a lot of really interesting things that you can do in that space. So I wanted to leave a lot of time for questions. If you guys don't have any, I can do some demos or something like that. But does anybody have any questions?
I was just curious what your Solr config or your schema XML look like. Is it just sort of a permutation of like some semantically important keywords that you used so that you can provide that functionality to your sort of your front end API?
It is. It's a lot of permutations of the things we care about, right? So if we have a string field, right, like maybe we need it to be indexed, maybe we need it to be stored, maybe we want norms or we don't want norms. All those different possibilities, you would end up with basically like say you have a string field. It might be star dot s for string underscore IS for index and stored, or I for index, something like that. So when we actually go to send the new field, we actually put these suffixes on the end, and then we run our search with those. We have a layer which actually will map a field name to one of these kind of internal field names. And then whenever we get results back from Solr, we strip the suffixes off and return the results to the end user. So from their standpoint, it's just the field name, but internally we're actually mapping it to all the dynamic fields. So yeah, just a long list of permutations for everything we need. And what we found is that once we got our list right, we hardly ever change it. I mean, there's basic search functionality people want, right? Strings, delimited text fields, free text fields, maybe a lemmatized text field, and then dates, things like that. So we do actually lose a little bit in terms of performance, in terms of, like let's say you have a date. How do you affect the precision, right? If you want, if it's a try field and you want the precision of 8 versus 4 versus 2, we don't have all those permutations. We settle on ones that are reasonable and say, hey, you use one of those. And if our index is bloated a little bit, it's okay because we are significantly faster at developing, and it's, for our use case, we would rather focus engineering time on other things and buy a few extra servers if we need them. In most cases, we don't. Now, if you're at Twitter scale, you're really, really concerned about the performance of the slightest little thing. But for us, I mean, we're large, but we're not so large that a couple of extra bytes is going to kill us.
My question is about, can you talk a bit more about the recommendation engine you talk about, where you use the runtime recommendation, and why, how do you implement that, and why you didn't go for the offline like machine learning, and how effective is that? Thank you.
Sure. I can talk a little bit about it. Effectively, I told you earlier, right? If we get a resume, we classify it. So we're gonna take the resume and say, hey, here's your most recent job title, and here's what we think that is. Like maybe it's a software engineer, maybe it's for search, maybe you used to be a traveling salesman, like whatever that is, we classify the document. So we have the actual text we're searching, but then we also have all of this meta information. So if we're trying to recommend a job to you, right, we can do it based upon the classified content. We can say, all right, well, here's what we think you are, and so we've got all these resumes that have been classified accordingly. We can do that. We can also do collaborative filtering, which is, right, like somebody applied to a job, and somebody applied to 5 jobs and someone else applied to 5 jobs, and they've got one job in between that's linking them. The person who applied to one set of jobs, we can say, hey, what did other people who applied to this job also apply to? And use those as the basis of recommendations. So that's kind of collaborative filtering, some classification-based recommendations. I can't talk too specifically about what we do because some of it's proprietary, but in general, I mean, those are pretty common approaches to doing recommendations, and we make use of those and a few others. In terms of why we do it real time as opposed to offline, it's a lot less processing. If you've already got your inverted index of all the things that you care about, it's easy to just execute a search query and get results. When people come to our site and they're taking different actions, we want to be able to update their recommendations in real time and show them, like, hey, here's your recommendations. Oh, you just applied for a job. Here's other ones that you might also want to look at. And so it's just really important for us to be able to do that in real time.
Can you talk about a little bit about the API? I mean, your effort to create a software API and as a SaaS for Solr. How you did that? Did you have to modify Solr in any way, or just a little bit about that?
Yeah, so from a philosophy standpoint, we take a very different philosophy than a lot of people here, I think, which is that we don't really want to customize Solr where we don't have to, right? Like I talked about having 150 some odd servers. When we have to actually go upgrade, install, redeploy those, it's actually a bit of a pain because you have to pull things in and out of the load balancer, you have to blast out, you have to reinstall, you have to do consistency testing, making sure you didn't break anything. So a lot of that can be automated, but at the same time, it's work. So as much as possible, we try to abstract the things that change out of Solr. So like I said, we've got one schema that everybody uses, which is dynamic and allows them to pass in whatever they want. But then also things like synonyms. We actually have a synonym layer, but it's outside of Solr. So before we send queries to Solr, we update the synonyms. And the reason for that, right, we want our business to be able to update synonyms in real time, to go to a database or go to a page that connects to a database, update it, and we want queries to immediately start using it. You could hook something into Solr, which externally reached out to a database and pulled synonyms in and reloaded cores or whatever, but that's painful. So for the cloud-like architecture, the things that we change are really more for things like scoring, which I talked about, and things like putting spam limits in, things that weren't kind of natively supported. But in terms of the cloud-like API, you could really do it without changing anything in Solr. Just make a bunch of dynamic fields that meet all of your use cases, create a wrapper around it in your application layer, which maps values and attributes to those dynamic fields, and then strip them out on the way out. And essentially, that's all there is to it. If you want to have a large globally distributed architecture, obviously you're going to have to build that separately anyway. So you could just tie this into that. But from the standpoint of just turning Solr into a kind of a software as a service cloud app, no, there's really nothing in Solr you have to customize to do that.
You mentioned that you store away these created dynamic schemas in a database, and I'd like to understand all the different ways in which you find it useful to have it there.
So we store them.
You said when you create this test schema, I believe you said that the schema goes into a database. Why is that useful? Where do you find that useful?
Yeah, so what we do, right, this API is generic, but if someone sends us a document without a schema, we don't know what that document is, right? And so what we actually do is when someone sends us a document, we XML serialize that document to save it in a persistent storage in a database. The reason being, right, if we decide that we want to do server maintenance, or we want to put you on new servers, or we want to shard you differently, right? You're growing too big, and all of a sudden we say, oh man, we actually need to add 5 more servers for this group. What we can do is actually offline add those servers, and then reload all of the documents and schemas and reflow them to the new search engine. And once it's ready to go, we can just swap them out behind the scenes. So for our end user, the cloud is always up, always running. The search team does have to do infrastructure-y things behind the scenes. It's not completely seamless when we hit scaling issues, but the reason we store it off into the database is so that here's my document, here's the schema associated with that particular document, and if I need to recreate it, I can, and so that's why we store them all off.
Thank you.
So coming back to your custom scoring function, I'm curious how you determine what bucket a posting belongs to. What are the factors that influence that?
Sure. So for us, let me go back to that slide. So you can actually, for this, right, let me see if I can abstract this out. Let's design engineer, it looks like a job title. So what we'd actually do is we would say, hey, the job title field is going to be bucket 1. And really great job is probably the job description, which is in our default bucket, which just gets a weight of 1, I guess. And then 10 years experience, we probably have an experience field. Career builder is company name. Design is something else. So usually it's fields that we're mapping into these. The reason being, right, you could actually create a separate field for each of those groups of content and send it to the search engine. But if you want to search across all of them, at query time, you're searching across 6 different fields. And if you have a lot of them, maybe you're searching across 20 fields. And that gets really, really slow after a couple of fields. So for us to be able to kind of add in as many buckets and different types of information as we want and maintain a constant query time, that's the way that we tackle it.
It's very cool. Thank you.
Okay. Yep.
You kind of touched on it already in terms of managing servers and load balancers and stuff, but could you elaborate a little bit more about how you're managing the clusters? 150 servers is a lot, so talk a little bit about your deployment strategy, and also, are you using like an active passive type system for disaster recovery, or things around that nature? Sure.
So we have redundancy everywhere. In our business, you can't go down, which is the case for a lot of you. In each data center, not necessarily in each data center, but we've basically got 200% capacity for everything. So if a cluster goes down in a data center, it's okay, we've got another one. Or we can fail over to another data center if we need to. If a data center goes down, it's okay, all of our other data centers can handle the load. So in terms of active-passive, we keep everything active, and when something has a problem, it just drops out of the load balancer, and we leave it out until we fix it, and then we put it back in. So whenever we do maintenance or anything like that, it's bring a cluster down, do whatever we want with it, bring it back up, make sure that it's healthy, and then put it back into production. So that we always follow that model whenever we're doing any kind of maintenance or redeployment or anything like that. In terms of our deployment strategy, for each cluster, we actually define in a config file which servers are, well, database, which servers are in what cluster. So when we go to deploy, we can actually pull that information in, and we have scripts which actually go do the install, change any specifics for that cluster, shard params, things like that, and deploy those out to the cluster, and then it's ready to go. One interesting thing we do is a lot of people deploy, I think most people deploy Tomcat, like their ops team will have Tomcat running on the server and they deploy Solr as a web app to Tomcat. For us, we've actually bundled Solr and Tomcat and everything needed except for Java to run it together. So for example, if a server goes down, I can actually take that install directory, copy it to another server and start Solr, and it works. So there's no, other than having Linux and having Java, the right version of Java installed on the server, there's really nothing else that our ops team is required to do. Like we actually deploy the full Tomcat plus Solr instance together, and it's the same across all the servers, with the exception of potentially some memory configuration differences for different cluster types and things like that. So our schema is always the same. We do have some slight things we have to do, obviously, for performance in terms of RAM allocated to the JVM, a couple of different Solr settings for masters versus slaves, things like that. But those are pretty much standardized. Yep. I think there might be time for one more question, if anybody's got it. All right. Thank you, guys. Hope you enjoyed it. If you have any questions, come talk to me afterwards.